Hello. Thank you all for joining us for the Q2 NVM Express sponsored webcast. Today's topic will be NVMe SSD management, error reporting, and logging capabilities. First, we'll introduce you to our presenters. Today, this webcast will be led by John Michael Hands, Senior Strategic Planner and Product Manager, Intel SSDs, and co-chair of the NVMe Marketing Work Group, Rohit Gupta, Segment Marketing at Western Digital, and Bill Martin, SSD I/O Standards at Samsung. Now, John Michael Hands will begin with an overview of NVMe technology features for errors, logging, and health monitoring.
Hey, good morning, guys. This is John Michael. So this kind of idea for this webcast kind of got started. We got an email from one of the press reviewers on asking some really basic questions on how do SSDs fail, and it was clear from the email that they thought the SSDs kind of fail like hard drives, and it was I got kind of inspired to write a blog post. We put it on NVM Express, and now it's one of the most popular blog posts that we have. So I now looking back, probably should have spent a little bit more time on it, but hey, that's why we're here this morning, to talk a little bit more about it on the webcast. And so I think there's a lot of interest in understanding how SSDs fail and all the features that NVMe has to kind of monitor and manage them. So just a quick snapshot. We are going to look at, this is just the latest NVM Express public roadmap that we presented at the NVMe All Members meeting. So I think if you go look on the NVMeexpress.org website, you will see NVMe 1.4 technical proposals that have been ratified. So the newest members of that are NVMe zone namespaces, key value, and namespace types. So that will all be part of NVMe 2.0 coming kind of later this year. And I won't talk too much about that today, but just to kind of frame where we are today, we have NVMe 1.4 as kind of the main NVMe Express specification for NVMe SSDs that runs on top of PCI Express. Then we have NVMe over Fabrics specification that runs on top of network fabrics, and then we have the NVMe MI, which is the management interface spec for in-band and out-of-band management of NVMe devices. So to start, how do SSDs fail? Well, I mentioned definitely not like hard drives. I think that one of the things people understand is SSDs are much more reliable than hard drives. Typical NVMe SSDs from manufacturers span from 2 to 2.5 million hour MTBF, or mean time between failure, which kind of corresponds to like 0.35 to 0.44% annual failure rate. So just in general, SSDs are already 2 to 10 times more reliable than hard drives, depending on what scenario you're in. So I've been a product manager for data center SSDs at Intel since our first NVMe drive, the B3700 in 2014. So I've got to actually look at many, a whole lot of data in the field actually on how drives fail, especially around NVMe drives, for product families that we've shipped multiple million units of, and I've kind of categorized them here on increasing prevalence. So on the right there, you have endurance, hardware, media failures, and firmware issues. These are actually, if you had a bar chart, a Pareto of like how SSDs fail, these would actually make up the majority of them, and mostly the firmware issues and slightly media failures and hardware. So endurance, I'll tackle the first one, where it's actually been a concern of a lot of people for a long time, right? Because SSDs have finite write endurance, where you can only write to them so many times before the NAND cells wear out. So people have been worried about it, but in reality, I think we really don't see very many returns for endurance issues. One, because NVMe technology, you can accurately monitor it with the smart, and there's lots of metrics to basically monitor it in real time. But more importantly, as the drives get bigger and your drive writes per day get higher, it's just less of an issue. Like for instance, our the Intel P4610 7.68 terabyte has up to 44 petabytes written of endurance. And we'll talk a little bit more about this in a few slides, but I just think the vast majority of enterprise server use cases, and even in the cloud, are not fully utilizing the endurance. The other thing about endurance, it can be accurately and predictively modeled. I helped write the endurance calculator on intel.com/endurance, but that's basically using measured data and kind of projected workloads to calculate the projected wear of an SSD. So endurance, not a huge issue. Now, hardware issues, you'd think that these would be a much higher prevalence of SSD failures, but They're actually not a huge percentage of the actual SSD failures because one of the things on hardware is that you can weed a lot of these out in validation and quality and reliability. We have reliability demonstration tests and quality teams that do accelerated testing with higher temperatures and humidity, and a lot of these can just be found in the long development process of the SSDs. So the really important ones we're going to talk about are media errors and firmware issues. So the media failures being like NAND problems. A lot of data center SSDs today contain kind of onboard RAID or an XOR engine to basically prevent from media failures and to hit a uncorrectable bit error rate goal. Typically in the data center side, like 10 to the minus 17 for uncorrectable bit error rate. And so typically you'd think that the media failures would be a much higher percentage, but really most of the mainstream SSDs can withstand one or even two die completely failing, and the SSD firmware can manage those failures pretty effectively. So and maybe this isn't common in data center SSD. For consumer SSDs, for instance, you might not see these types of advanced features, but the most important thing we're going to talk about as far as some of the things to monitor the errors are looking at firmware issues. So SSD firmware is super complex, and it takes many developers many human hours to develop this complex firmware to manage the data, make sure the data integrity is correct, make sure you cover all corner cases and all commands and every type of corner case on every type of system. So firmware issues actually make up the majority of SSD failures. And you'll see when we go look into the NVMe features, we have stuff like telemetry to go help SSD vendors and OEMs and system and cloud service providers actually help root cause those firmware issues to help get better data integrity and better reliability in the field. And so this is my PSA to everybody out there. If you are SSD vendor or OEM issues a firmware update, please update the firmware. That's the number one thing you can do to significantly reduce SSD failures over time. The return category is things that you can see that we have SSD monitoring and NVMe to help kind of monitor some of this stuff. But if you have over temperature or you have a timeout where the SSD took a long time to respond, somebody might see that as a failure, but there might be nothing actually wrong with the drive. It could just be a system incompatibility. Somebody might see a performance problem and they might return the drive. So those are just kind of not really hard failures, but we would maybe classify it in the returns or annual return rate. So there are some really good case studies on this. I can't go through all these in gory detail, but this first paper was written by my colleagues at Intel. A lot of the smartest guys I've worked with in the SSD development side, and they've pioneered a lot of the stuff on silent data protection and uncorrectable bit error rate and this onboard RAID for SSDs. But this paper goes into the failure mechanisms for SSDs, like different types of errors, how they classify silent data corruption versus just uncorrectable bit error. There's case studies on actual reliability demonstration tests from Intel and field AFRs from our old, most popular SATA SSDs. So even though, the Pareto of failures may look very different from NVMe drives today, it gives you kind of a good idea of how we thought about this, how we run our reliability demonstration testing, how a major corporation does quality testing, how do we ensure that, SSDs are going to meet a certain, quality standpoint. And it really does talk about how all the possible ways an SSD could fail. So I think this was helpful in thinking about this for NVMe. And the next study was a study of SSD reliability in large-scale enterprise storage deployments. So this is really interesting. This was from NetApp, and they sponsored this with 1.4 million drives in the field that they collected telemetry and smart data from their ONTAP. Although most of these drives in this study were SAS, we can basically learn all those lessons into helping us develop NVMe software. You'll see basically directly correlates to the lessons on NVMe. Some of the stuff I'll talk about was, basically one of the things they found was our observations emphasize the importance of firmware updates, as earlier firmware versions can be correlated with significantly higher failure rates. So basically correlating what I just mentioned, which is SSD firmware is really complex, and it's one of the most complicated things and one of the highest failure rates. And then the other thing was that larger capacity drives seem to correlate to larger failure rates. They suggested that there might be more media failures, but my hypothesis is that the SSD firmware on large drives are just much more complex. There's many more corner cases. And then the other thing that interesting that came out of the study was correlating to what I just had on the previous slide, which was, hey, most think they said something along the lines of like 99% of users use less than 15% of the endurance of the drives, and I think the mean wear on most of the drives was like less than 4%. So you know, very single-digit wear on 1 and 3 drive write per day enterprise class SAS drives. So just kind of correlating what I just mentioned, even in enterprise storage workloads, you know, most customers are not, you know, running into endurance problems. The third is really interesting, which is from Brendan Watt, who's a principal engineer at Microsoft on Azure SSDs, who I had the pleasure of working with at Intel for a very long time doing NVMe stuff. And his presentation at Flash Memory Summit, I think it was 2018 or 2019, talked about how to use smart and advanced log pages to do predictive failure and failure detection and analytics on drives at scale. And we're going to talk a little bit more about this in a few slides about some of the new stuff that's coming in NVMe, outside of NVMe, to help do this. So this is my dashboard of kind of all the mega features. Rohit is going to go into a little bit more detail on some of the actual, you know, even more log pages in this. You know, I think obviously the best way to learn about all this stuff is just to pick up the NVMe spec. I know it's not organized in a way that's, you know, has all the error stuff in one place, because really this is a core part of managing SSDs. You have to be able to understand, you know, the SSDs. So the smart log page, this is kind of your main dashboard for health monitoring. I'm going to show a snapshot on the next slide, but the main thing on smart is basically the critical warning bit. So that's if a lot of customers just ask us, hey, we just want a yes or no, is the drive good or bad? The critical warning will light up, and it has a bit that will tell you like if there's something wrong with the drive, if it's over temperature, if there's significant media errors. So if you were to monitor one thing on an NVMe SSD, it would be the critical warning. The error log page is just the log page that maintains a log of the errors, you know, basically what queue they came from, which namespaces were affected, what type of error, and then some vendor specific information. But that way, you know, if there are errors, they get logged in the log page. The persistent event log, this is one of the ones that new in NVMe 1.4. We're going to talk a little bit more about it in a few slides, but think about this as the human readable SSD log. It's like the black box recorder of all the things that happen on the drive with timestamps. And so an operating system or other host software could actually go back and figure out what's wrong with the drive if something happens. So we talked a little bit about why, you know, firmware failures are one of the main contributors to SSD failures. So telemetry is actually one of the most important features in NVMe, because it allows you to dump telemetry logs from the drive, which could be health statistics and monitoring, but mainly you know, assert logs or dumps for when an SSD fails, and they can send that back to the SSD vendor. They can figure out what happened and root cause it, and then fix the firmware and make it better for the future, so that that kind of failure doesn't happen again. Asynchronous event support, basically a way to notify the operating system if errors happen or anything happens. So that's usually the errors as well, to be able to asynchronously notify the host. Device self-test, I do have a slide on this. We're going to talk a little bit about this, but if you think about basically being able to run an offline diagnostic test, you can use it in like factory integration or testing, or as a system integrator to basically figure out if a drive is good or bad. And many customers just want the ability to run a quick test and say, is this drive good or bad? Yes, yes, no, okay. End-to-end data protection, you know, we won't have time to talk. This could take an entire webcast because it's so complicated. But basically the way, it's basically preventing against data corruption by adding data protection and protection information to the bits, of providing CRCs. And a variable sector size, you can actually provide metadata and ECC data into the data itself. So lots of stuff in NVMe. Again, there's so many features in NVMe, but these are some of the most important ones for errors, logging, and management. You know, the NVMe has an entire management interface specification, which again, we have a whole webcast on this, so I'm not going to go into it in detail, but we have in-band and out-of-band management, you know, through NVMe MI, the management interface, typically done out-of-band through the SM bus, so you could have an operating system agnostic management console to basically manage the SSDs. But, so this is a snapshot of a NVMe smart log and an error log. I just took a screenshot. I grabbed one of the drives, a Intel SSD P4510 from our validation, just to show what it would look like with, you know, something that had gone through like a robust validation. This drive I grabbed probably went through like, you know, 100 different firmware versions and, you know, hundreds of hours of validation. You can see, so if media errors were to show up, you can see it there. You can see the critical warning bit 0, nothing's wrong with this. You can see the temperature snapshot there, available spares. Anyways, you can look at the NVMe specification to look at all the log pages and all the editings in a smart log. But think about the smart is really your main dashboard for what's going on with the drive. And then the error logs, you can see there's many error logs. If there were errors, you could do a grep, simple grep command with the NVMe CLI, which I'm shown here, to basically find out if there are any errors. I'm just reading the first log page, and you can see there's no errors here on this drive that I'm checking out. So telemetry, I mentioned, this is really actually one of the most important features because it prevents against firmware issues. And if there are firmware issues and a drive fails in the field, you can dump a telemetry log and send it back to the SSD vendor to go figure out what happened. There are multiple, there's a host initiated and a controller initiated, which is the drive initiated. And for the data area, there are three different sizes. You may want to use the first one for kind of like periodic pulls like health monitoring or performance. Now, the telemetry spec in NVMe doesn't define what's actually included in the payload. It just tells you how to read the data and then, where it's located and how to read the different areas. So the SSD vendor and, system people, the OEM can actually help specify what goes actually into these telemetry logs. But really, they're designed to help the SSD vendor go, pull a log when a drive fails in the field and bring it back to them so that they can understand what kind of problems there are. That's kind of the main use case. There are other use cases for the telemetry log pages that I don't have time to get into here, but it is one of the main features for this in NVM Express. The other one I'm going to talk about quickly is device self-test. So this is an offline diagnostic test. So when I first heard about this feature, I thought it was stupid. I was like, hey, SSD firmware is kind of checking all this stuff in real time all the time, right? We have to know if the data is good or bad and the consistency of the data at all times, to be able to ensure to the host that the data is correct and the drive is functioning correctly. The drive would have a very hard time running if these things were not running. But now the more that I think about it, I think this is a very good feature. After I've spent some time learning how it really works in some of the use cases, but some tests are better to do offline, right, where you're basically saying you can't run any other commands while you're doing this test, so it's an offline diagnostic test. And the short test is just 2 minutes. This is what's in the specification that just basically says, here's what's in the specification for, a sample test of what you may run would run the RAM, smart check, volatile memory backup, NVM integrity, data integrity, metadata, stuff like that. You can run a long test too. The short test is supposed to be 2 minutes or less. The extended test can be a little bit longer, and you can't interrupt it by a format or sanitize for another self-test command. So again, this is just a simple test you can run. Is the SSD good or bad? Making sure you can do an offline diagnostic test to see if the drive is running correctly. So I'm going to spend my last 3 minutes talking about something kind of interesting. There's an OCP Cloud NVMe spec that was released. Facebook and Microsoft presented it at the Open Compute Virtual Summit this year, and they had been talking about it in the Open Compute Storage Workgroup. But really, this is there's a lot of confusion about, hey, why do we need more NVMe specs? Don't we already have an NVMe spec? Well, they've done some really cool stuff. They've taken a lot of the good stuff that's been in the Facebook custom firmware and Microsoft custom firmware that they've had for many years with SSD vendors and kind of put it into an open source standard spec. And this is some of the stuff that's kind of included in the spec, stuff like form factor going into EBSFF and some of the new things that are coming. But really, I'm going to talk about two really interesting things about this error, which are these vendor unique log pages for cloud SSDs. And the first one is this C0 log page. And one of the things that you can, in this presentation, there's a link to the actual spec. You can go read this. But one of the cool things NVMe allows is vendor unique log pages. So this log page C0, an SSD vendor can implement this, and then now it's in an open source OCP Cloud NVMe spec that basically gives a lot more detailed LAN information and SSD error information than you would find in the typical SMART. And with this type of data, I mentioned in that first, when I was kind of looking at those case studies, this is the type of data that a large hyperscale vendor would actually use to go do predictive analytics and AI and machine learning on these types of logs to go be able to predict failures and figure out at large scale in drives, how to correlate failures between different firmware versions or different drive vendors or all kinds of different things. So a lot more detailed information, and allowing this in an open source specification is going to really help push the industry into the right direction for this. So I encourage you guys to take a look at it, but there's a lot of interesting stuff in here about, and they've specifically picked some really interesting things that can help do even deeper predictive analytics on SSDs. And the other thing that they've added is the C1 error recovery log page, which I really like because I mentioned, if firmware failures do account for the majority of SSD failures, the ability for an SSD to actually recover from firmware issues is actually a huge deal. So this error recovery log page will actually have the ability to be able to, the drive during a failure can actually tell the host, hey, if you just reset me or format me, I'll be all back to normal. And you could even significantly reduce SSD firmware failures in the field. And this is a really good idea, especially when we get to talking about really big drives, as we have 15 terabyte drives in the industry today and 30 terabyte drives next year and even higher in the plans, exponential capacity scaling in the future. It's very important to be able to gracefully recover from failures. So I'm out of time. I'm going to be passing off. Bill is going to talk a lot about Rebuild Assist, but before Rohit is going to talk about some of the other features. These are just all the NVMe 1.4 features, but the ones that we're going to specifically cover today are Rebuild Assist, because that's one of the new ones in NVMe 1.4. After Rohit kind of covers, he's going to go, this is the persistent event log, and don't worry, he has a better slide than I have that kind of goes through the persistent event log, what it's used for, what kind of different information's in there. So that's it. I'm going to hand it over to Rohit. Thanks a lot.
Okay, can you hear me, guys?
Yep.
We can.
All right, perfect. All right, so thanks, John. Let me build up some of his thoughts and presentation points. Just keep clicking the slide, next slide. Okay, all right, good. So let me build up on something that John presented. So let's go back in the history and let's talk about the errors that we have with storage devices. So in a typical large-scale data center deployments, we have hundreds and thousands of storage devices deployed, and they are quite different from the magnetic media counterpart. The errors might be different, the failure causes might be different. How do we track it? How do we capture it? And moreover, when the vendor asked to look at the specific data sets, particularly about the failures and errors, how do we make sure there's no private data or nothing is shared except the required data? So that's one critical part. Other is, how do we standardize it? Like across the vendors, the similar or same information is passed, which is required to check and solve the problems. So, and as well as don't run into some legal challenges when it comes to the data privacy and all that. So there was a standard required, some sort of the format, standard, and what kind of information is needed for the vendors to resolve the problems and figure out if it doesn't happen next time, as well as do a lot of automation, like trigger certain key points if something goes wrong, what is the next step to do for a storage device. And that's where the NVMe comes in. If you look at the NVMe 1.0 spec, that was a simple set of commands and only NVMe and the PCI Express interface. But as soon as the interface and the devices getting matured and deployment started increasing, you can see that the NVMe PCI on the PCI Express and then the RDMA capability over the fabrics. Not only Ethernet, look at the fiber channel, look at the InfiniBand, and a whole new form factor evolution. All that things started coming up, and as a result of that, the commands, the admin commands and NVM commands, they have started proliferating. Like more and more is desired, more and more information is requested from the drive, so that people can debug and find out the useful information. So that's the context. And it's getting complex as the capacities are increasing. The NAND is shifting from the MLC to TLC to QLC. Controllers are getting more complicated. So all that is really challenging. So I'm touching base on some of the key aspects of the NVMe 1.4 spec. This is largely taken from the section 5 of the NVMe 1.4 spec. On the left-hand side, you can see the chart represents what commands are possible, admin commands are possible. So one important note is if I pick up one single command, we can spend hours and hours talking about just one single command, and we don't have enough time to go through every single detail. So I thought of like presenting what do we have, and interested folks can go and look at the 1.4 spec in detail, and if they have questions, they can always reach out to us. talking about specific commands like get log page, device self-test, where the failures like fatal errors, interface challenges, anything to do with the state machines, the code dumps, all that is possible to capture. It's influence event about the health and temperature issues, the drive is failing and leaving some critical errors, critical warnings. We should be able to read that and automate a lot of processes. Going forward, the NVMe spec is maturing and giving a lot of new feature sets like namespace and namespace management, virtualization, and John talked about the NVMe MI spec. So all that is kind of evolving and getting more and more complex things. So for example, namespace attachment and management. It talks about how to attach and detach and manage the namespaces with the controller. Virtualization is like how to allocate the resources, the flexible resources to a primary controller and secondary controller, and make sure the same set of hardware can do more with little set of the drives. And really, this is so enriched. This is so much powerful as compared to the previous generations. Like a lot of capabilities have been added, and Western Digital is keep on talking about more and more information that can be fetched from the drive and helpful for the engineers to go and debug it. Some of the commands like the identify command is a set of features that we can look at, and the controller and the namespaces, all that can be identified with the NVMe identify command. Then we got the send and receive commands and the namespace management we touched base on earlier. And the get and set features, you can see a whole lot of things that we can do with the get and set features. And then this is the interesting one, the get log pages. So I'll touch base on the get log pages a little more on the next slide. Yeah, so this is starting with what we can do with the get log pages. The error correction, error information, all those events that have been captured if the host is requesting the previous error logs, then drive is able to give all the information back. The information is not persistent, data is not persistent. Every controller level reset, the power reset, the power cycle, the information is gone. But in the persistent event logs, some of the events and some of the data can be saved there. Smart, I think it's pretty known in industry-wide. Smart can talk about the health, the endurance, the bad blocks, the life, what was the performance across different workloads. All the information can be captured via smart features. And the next one is about the namespace, changes in namespace management. That the controller can look at the attach and detach process and the management of the namespaces. Okay. Yeah, so we talked about the change and change namespaces and the attach and detach process. The device self-test, we talked about the fatal errors. We talked about the NAND media issues. And they can be various vendor unique device self-test. We can track the progress of the device self-test. You can look at, you can capture the events and see what kind of failures happened or what kind of events captured, what kind of warnings captured. Telemetry is an interesting area where the data, either the host can request the telemetry or the controller can initiate the telemetry request and provide the useful information about the drive warnings, about the drive failure over the life of the drive. There are different areas. I think they call it DA1, DA2, and DA3, and they can capture the different type of information there. I think Western Digital is requesting to the standard committee, like, can we increase that size, because I think the current proposal is not good enough to support the debug information. So we need to go above and beyond what we do today. So that will be helpful in terms of providing more and more information to the vendors and to enhance the debug capabilities. All right. The endurance group information, I think this is about the endurance group and the NVMe sets. We can look at that information and figure out any critical warnings or any possible issues there. Okay, the next one is the persistent latency side. So I think one of the things that we might be aware of, the drives are known for the wear leveling and garbage collection. So any I/O that comes in, and in order to give the predictable latency, somehow the drive has to stop the any background work and allow the I/O to complete it. But there is a certain time we can stop the background activity, and beyond that, the drive has to go back and start the garbage collection same time we do the I/O activity. So what this feature does is give us the time window, as well as how many events occurred in the past, and how much is the window left for any predictable latency, so that the host can choose to give any predictable latency mode to this drive, or choose the option for the drives. Maybe drive A is having only like a couple of seconds left for predictable latency mode before the garbage collection wear leveling comes in. So it might be a better idea to give the IOs to the other drive so that they can fetch the data at the end, offer the predictable latency mode. I think the other one is asynchronous access. So imagine we have multiple namespaces and different controllers have different sort of access. Maybe some of the private, some of the namespaces, some of the resources like private consumption. So there may be asymmetric access across the controllers, like in terms of performance, in terms of latencies, in terms of some of the namespaces may not even offer the access to some specific controllers. So that asymmetric namespace access information can be passed on to the controllers like, hey, dude, you don't have the access to go and get the data from this namespace, or maybe you can only utilize a certain level of the performance. You can only have a certain level of the latencies. So all that information can be passed to the controller so that it's a level set or the expectation set in terms of what it can do or what it cannot do. And perhaps the last one is the persistent log page events. Like it captures the events, it captures the data where it can retain it across the power cycles. The endurance group information, or this. Okay, so the persistent event log, it captures the event about the firmware commits, talks about the smart health snapshots, the power around its information. There are some vendor unique features that can be captured from persistent log events. There are information about the sanitize start, sanitize command, and there are get and set features, the thermal activity, and telemetry. So that is the useful thing. As I said earlier, it is not possible to cover all the Spec 1.4, Section 5. This is too much detail. I suggest the viewers and the active people to go and look at the Section 5 of the Spec 1.4. It has a lot of details. With that, I pass on to the presentation to Bill Martin. He will talk about rebuild assist. Over to you, Bill.
Okay, thank you, John Michael. Thank you, Rohit. So you've heard a lot about why there are errors on SSDs, what the failure modes are, or at least some of them. You've heard a lot about the different ways that you can access that information. But once you have an error, what do you do? So I'm going to talk about a tool that is out there, a mechanism that is out there within the specification to try to alleviate some issues with your drive so you can keep using it, so that you don't, when you see you're having errors, just immediately go and ship your drive back. There's one concept that I didn't put a slide in that I realized is important to understanding the remainder of the rebuild assist. And that is the concept that where you have errors, they affect logical blocks. The logical block in today's SSD is your primary unit of storage. A logical block is stored on a physical block in a disk drive. If that physical block goes bad, then you can't access that particular logical block. But if you write that same logical block again with the same data or new data, that logical block all of a sudden becomes readable again because the drive stores it on a different physical block. So the concept there is that you don't have a fixed mapping from your logical block to your physical block address space. So with that, let me get into the Rebuild Assist part of this discussion. So Rebuild Assist is a feature. It is actually called the Get LBA Status feature. That feature has two parts to it. There is the LBA Status information, which is a log page. This log page is updated when bad LBAs are discovered in the background. So on the next slide, we'll kind of go into how you discover the bad LBAs in the background. This log page, when you update it, may actually generate an asynchronous event notification. And we'll talk about that a little bit more in detail as we go through this portion of the presentation. Once you have that, or if you want to just try to monitor the health of your device, then you can use the Get LBA Status command to get a list of potentially unrecoverable logical blocks. And you have tracked logical blocks, which are done in the background by the drive. And then you have untracked logical blocks, which are a list of logical blocks that are found when the host requests that you go and scan for them. So, tracked versus untracked. So tracked LBAs, they're detected by the controller during normal operation. How does it do it? Well, it can do it through background scans that it chooses to do that are not commanded to be done, but just part of its normal operation. It can detect a component failure. When a die on your SSD fails, it can detect that that die failed and say, you know, any LBA that is stored on that die is going to be bad. A read request from the host can go and read a logical block, and you get an error when you attempt to read it. That can generate a detected bad logical block. These tracked logical blocks are retained until they are repaired. And what does it mean to repair them? It means they're removed when the host writes to that LBA. Again, when you write to it, it gets stored to a different physical block. Untracked logical blocks are generated when there is a scan requested by the host. A scan may take a long period of time because what you are being asked to do is go through your mapping tables in a sequential order of logical blocks and check each logical block to see whether or not it is readable. So this is a time-consuming process, but if a host believes that there is some issue with a SSD, it can go to discover which logical blocks may be bad. The blocks that are found through this process do not have to be retained following reading of the list of potentially bad logical blocks. So what do you do with it? So the Get LBA Status Information Attributes feature, it requires that you have the LBA Status Information Notice asynchronous event. This allows the controller to notify the host when it has asynchronously discovered things. It requires that you support the Get LBA the LBA Status Information log page, and that you support the Get LBA Status command. So the LBA status information log and asynchronous event notification. Entries are added to the log as long as there is not a pending asynchronous event notice for this particular event, for your LBA status information log. Okay, and what this means is once I generate an AEN from the controller to the host, I will not continue adding new entries into that log so that the log page stays constant while the host attempts to recover those bad logical blocks. The log has a number of elements describing where there may be bad logical blocks. So these elements describe a range of LBAs. And it doesn't mean that everything in that range is bad. It means there may be something bad in that range. And therefore, what you want to do is go scan that particular range to determine if there are any bad LBAs. If there are bad LBAs, then you have, if you're in a RAID system, then you can recreate that particular piece of your RAID stripe for that logical block. If you are in a mirrored system where you have multiple copies of your data, you can go out to your mirror and find that data and rewrite the data, thereby making the SSD that had bad logical blocks now completely functional. Okay. The asynchronous event notification is generated when there are elements in the LBA status information log and one of two things has happened. One is a host specified interval of time has occurred. Now what this is doing is saying, I may not want to know immediately every time the controller detects a bad logical block in the background. I'd like to, wait 5 minutes in between notices and then get a notice, go out, do my cleanup work, and keep running so that I'm not getting interrupted extremely frequently. The second condition would be a controller-specific threshold number of elements have been added to the log. So the controller may have a threshold that says, when I've added 25 bad logical blocks, I need to inform the host that it's got quite a few, even if I haven't expired the time that the host has asked me to wait. So in either of those events, I generate a asynchronous event notification to the host. So the LBA Status Command has the get LBA status parameters. And these, you have an action type. The action type tells you either return tracked LBAs, and this one, somehow I got the scan for on the wrong thing. So you may return the tracked LBAs, which are already there, or you can scan for and return untracked LBAs. Okay, and the scan is the thing that may take time. The host may ask you just to scan a small portion of the drive at any given time, or a small portion of the LBA range at a given point in time to limit how much time it takes to do that. So the untracked LBA list may be generated in increments. And that's what I was just saying in terms of the host can ask for segments of that. So what's the recovery procedure? Well, on tracked LBAs, the process here is the controller sends an LBA status asynchronous event notification. The host reads the LBA status information log page, which informs the host what the ranges of LBAs are that may have bad LBAs. The host performs get LBA status commands on those ranges of LBAs that may have bad LBAs. And then the host goes and gets the good data from its alternate source, be it a rebuilding it from a RAID or going out to a mirror copy, and it then writes those bad LBAs. For untracked LBAs, this is the host basically going and saying, I want to check this SSD out. So it goes and performs get LBA status commands to proceed through however much of that SSD it wants to query. And if it finds LBAs, it does the same thing as in the tracked LBA process. But in the untracked LBA sequence, there is no asynchronous event. There is nothing in the LBA status information log page. It is simply the host determining that it wants to go out and query for bad LBAs. So let's go through an example. So in this example, the controller detects a die failure and namespace 1 and namespace 2 are affected. So what it has is in namespace 1, and it has an LBAs in the range A through B and C through D. In namespace 2, it has LBAs in the range A through Z. So the controller updates the LBA status information log page with that information and issues an asynchronous event. The host reads the LBA status information log page. It gets the information about the fact that the LBA in range A through B and C through D, if it's working on namespace 1, have potential errors, and in namespace 2, that in A through Z there are potential errors. So at that point in time, the host issues a get LBA status command with a type of 11H for namespace 1 for LBAs A through B, for namespace 1 for LBAs C through D, and another one for namespace 2, LBAs A through Z. So when it has done that, it has gotten a list of actual LBAs that have issues. The host goes and gets the data that should have been in those and writes each of those LBAs that are returned from that get LBA status command. And now you have recovered your drive and you have data. If you are the mirrored drive, now both of your mirrors are good. If you are one stripe of your RAID, then all stripes of your RAID are back to being good. And the controller at this point removes whatever LBAs were written from the tracked LBA list. So rebuild assist I apologize. I actually got these named backwards in here because what we just went through was actually the tracked list example. And what we are going through next is the untracked list example. So the host issues a get LBA status commands for namespace 1 with type 10 hex. The controller scans the indirection table to find the untracked list. That untracked list being any LBAs that it found through this scan that actually have potential problems. And it then returns that untracked list to the host. And at this point in time, so in this particular example, the untracked list had LBA A, LBA F, and LBA Z were each shown as being bad. So the host in this case rewrites LBA A, LBA F, and LBA Z. Okay, and then the controller removes the LBAs from the tracked list if it happened to track them. It is allowed for the controller following a untracked request to retain that information or choose not to retain that information. So through this process, you have been able to find where you had bad LBAs on your device and restore those LBAs with valid data from an alternate source. So with that, I'd like to turn it over for questions and answers.
Thank you, John Michael, Bill, and Rohit, for detailing the features used to make NVMe SSD management simple. So now we'll begin the Q&A portion of the webcast. If any of our viewers have questions for our experts, please submit via the BrightTalk chat feature. The first question we'll kick off with is, what is the observed real-life BER for the PCIe portion of the NVMe drive at Gen 3 speed?
Yeah, the way I read the question, I mean, you can go to the PCI Express base specification for what the raw bit error rate is supported at the different interface speeds in PCIe Gen 3 at 8 gigatransfers per second. So, yeah.
Great. Next question, what indicators can be used to assess problems with the physical media? And where can things such as CRC errors be read?
Yeah, this can go into the log page, the get log page, the smart health information log. There are media and data integrity checks available.
You got it. Yep. So what Rohit said, in the smart media and data integrity errors, CRC errors should be, or checksum failures should be logged. Now PCIe CRCs, that's slightly different. That's eCRC, and that may be, some of the PCIe eCRC errors may not be accounted for in the NVMe smart log.
Next question, after scan, if LBA Status Command identifies untracked bad LBAs, does a mechanism exist to recover any stored logical or physical data associated with these LBAs once SSD is removed from the original system?
So basically, when a LBA is marked as bad, what it means is that the controller was actually not able to read the data. So whether you leave it in the system or take it out of the system, until that logical block is rewritten and stored in a different physical location on the SSD, the data that is there is not recoverable, and that's why it is marked as a bad LBA, to allow the host to go to an alternate source for that data, recover it, and write it there into that LBA space again, restoring it.
Yeah, and I know we didn't have time to go over all those use cases, but in that one of those studies that I alluded to, the NetApp one, I think they had some really interesting information on like torn writes or misplaced writes where they have a CRC error at the file system level and they don't know, hey, did the drive cause that? Was there some other software in the stack that caused that? We don't really know, but hey, let's just take this drive out. And stuff like Rebuild Assist can be used to help say, okay, is the drive does it actually have an error, and can we go rebuild the data without having to completely scrap the drive and have a field replacement? So.
Great, thank you for answering. Next question, is the failure log telemetry information protected and still available in firmware panic?
Yeah, I'll just say I think that's the intention. Yes, for sure. Is even if the namespace is down and the namespace gets prohibited from read access because of a logical failure, the NVMe controller should still be able to accept admin commands and dump the telemetry log. Yeah, that is definitely the intention. Yeah.
That's right.
Does the NVMe Specification 1.4 support PCI Express Gen 4 line rate and protocol stack?
Yeah.
Yes,
it does.
it sure does.
Yes.
And that's, I think maybe something missed that's maybe it's super clear to me and not everybody else. But yes, PCI Express and NVMe Express are separate specifications. The NVMe spec runs on top of PCI Express. So when PCI Express gets to either different form factors or higher link speeds like PCI Express 4.0 or 5.0, there actually isn't any changes required in NVMe Express to make that work. That's one of the things that why NVMe picked PCI Express as the scalable interface is because of that.
It can support not just by 4, it can go 2 by 2 interface as well. So we can split the dual port architecture, 2 by 2, 1 by 4. All that is possible with PCI. Which in the other language is scalable architecture with that. With the card form factor goes all the way to cross 16. In certain form factors, yes, but not all of them. The cross 8 in the adding card form factor, if you start taking up the bigger form factors like full height cards, maybe all the way to cross 16.
So there's a question about is there any error logging design for SI related issues, for example, getting I margin, etc. The PCI Express 4.0 specification includes built-in lane margining, but that doesn't have anything to do with NVMe per se.
NVMe, yeah, that's a PCI spec, not the NVMe spec.
What indicators can be used to assess problems with the physical media, and where can things such as CRC errors be read?
So I think we answered this question about the smart log. It has the CRC and the checksums there.
Yeah, and I think the first part of that question is, hey, if physical media is bad, then there should be media issues that come up on the smart log.
Yeah.
If there's something, like the example was PCB etch issue, if something like that caused an intermittent signal glitch or something, that actually may manifest itself as a firmware issue or a timeout, not necessarily just an error. But yeah, again, the question you ask is, we see all kinds of different weird stuff, and that's part of what validation and quality. All three companies on the phone here have pretty robust quality standards that that catch stuff like that.
Yeah. In addition, now picking up the PCB edge, what kind of problem that will result into entirely depends where to find the reasons, where to find the logs is based on what kind of problems it lead to. Stating the PCB etch issue, that can be a signal integrity challenge which goes into the PCI spec. If it is the media problem, that goes to some other location. So it really depends what kind of problem that is going to lead to.
All right, being mindful of time here, we're going to go ahead and wrap this up. We want to thank our viewers for participating in the Q&A portion. Just so you know, this webcast has been recorded and it will be posted to the NVM Express YouTube channel for viewing, and the slides will also be uploaded to the NVM Express website. And if you'd like to keep up to date on NVM Express news and announcements, we encourage you to follow the NVM Express Twitter account at NVM Express. And on behalf of NVM Express, we want to say a final thank you to our presenters for contributing their expertise.
Yeah, thanks, guys. I know I'm seeing a ton of questions come in too. Unfortunately, the Bright Talk thing shuts us down, but we'll figure out how to open up a blog where people can ask a bunch of random questions about this stuff, because I know, I think it would be a good use of our time to help get everybody's questions answered. So we'll figure out a way to do that. And yes, the slides will be posted. We'll post them up to nvmexpress.org.
Thank you all for your time.
Thank you all for attending.
All right, thank you.
Thanks, everyone.
Okay, bye-bye.
Bye.